Hi, welcome back. I want to talk about the other most common potential energy for us, and that's going to be potential energy that is stored in a spring. So we have a spring here. It would be an ideal spring. We can do non-ideal springs in Physics C, but we'll wait till you guys get that calculus and go back and do it. But it's pretty easy. This is equal to negative kx, or the absolute values, right? Because the force in the spring and the displacement are always in opposite directions. I compress it. I store some energy in this spring. When I let it go, this energy can be transferred from spring energy to kinetic energy. This shows us the displacement and the force being in the opposite direction and gives us our Hooke's law spring constant, which we talked about in F net equals 0. All right, so this is going to be given as 1/2 kx squared. On our equation sheet, it's going to be a u with the subscript of s. K is going to be the spring force constant for that specific spring. X is going to be how much it is stretched or compressed. So they give us the spring force constant of 670. They also tell us how much it is stressed or, in this case, it's compressed. So I'm just going to take 0.5 times 670 times 0.9 squared. Gives me about 271 joules. So that's how much energy is in the spring. It's potential energy because I could get it back out by releasing the spring. All right, so in these problems, if you remember, we talked about force distance graphs, and we said that the area under the curve was the work. Well, work is also the change in energy. And so if I look at this spring, when there's no weight on it, no applied force on it, it's not being stretched or compressed. As I put this force on, it causes it to stretch or compress. This is linear. That makes it an ideal spring. The area underneath should be the work or the energy. The area of this, because it's a triangle, is going to be 1/2 base times height. The base is the distance that it compresses, which is x. The height is f. If you remember what f is equal to kx, right? Because it's the spring force. I know that was negative. I know those are absolute values. It really doesn't matter because you would decide whether it was positive or negative energy based on how much energy did I put in the spring, how much work did the spring do, those type of things, the direction of the force to the displacements relationships. So if I rewrite this as kx, I get 1/2 x kx. I get 1/2 kx squared. This is the area underneath. In calculus, it'll be known as the integral. So if we have some other function where it isn't linear, we'll be able to use calculus to find out what that area is and say, yes, this is how much energy is stored in it. It's also how much work I did on the spring to put that there. Ooh, I don't know why that didn't work.